This is the final video on chemical formulas, reactions, and stoichiometry. The focus of this video will be the stoichiometry. We're going to cover all the different types of stoichiometric calculations, as well as an application of them called percent yield. Let's discuss what stoichiometry is. Stoichiometry is using chemical equations to calculate how much you have of something from something else. A lot of times you're going to be given a reactant and asked, how much product can you make? We're going to use our balanced equation knowledge and combine those balanced equations with molar conversion. So really taking everything we've learned within this particular PowerPoint, within this particular topic, and putting it together. This here is a visual that really seems a lot more confusing, I think, than it ends up being once we go through some practice problems. So the first thing that's really important in stoichiometry is that we're going to assume that the coefficients within a balanced equation always represent the number of moles you have of each substance. These are often called mole ratios or sometimes mole bridges. So for example, I'm going to take my balanced equation and I'm going to turn it into a variety of conversion factors. So for every 1 mole of N2, because N2 has a 1 in front of it, I have 3 moles of H2. For every 3 moles of H2, I have 2 moles of NH3. And I could write quite a few others, but basically just taking those coefficients and turning them into conversion factors. So the first type of stoichiometry that we're going to do is called a mole-mole problem, because it's going to provide you with moles of one substance and ask you for moles of the other. That's how you know that it's mole-mole. The general equation is provided below. It's going to be the given number over 1, just like normal for our dimensional analysis. And then what I like to call the balanced equation step, because I use the balanced equation to help me out. And it's going to be the coefficient of what I'm looking for over the coefficient of what I was given. So these are only 2-step problems. We'll do an example on the next slide. So here's our first example, and then you guys will get a chance to try one. It says how many moles of O2 are produced when so many moles of Al2O3 decompose. The first thing you're going to want to do is balance the equation, because with an unbalanced equation, you'll get the wrong answer. So I'll do that real quick for you. So now I'm going to solve the problem. My given is the only number provided in the problem, so my 3.34 moles of our Al2O3. It's really important that you label the substances here, primarily because we're now converting from one substance to another. Before, we were really just converting, from grams of NH3 into like liters of NH3, so it was the same substance. Our second step is the balanced equation step. You don't have to label it BE, but I like to because I find it helpful to remind me. So the question's asking us about oxygen, so that's what we want. So we go to our balanced equation and we see that we have 3 oxygens, so 3 moles of O2, and we're getting rid of our given, right? So we're still doing dimensional analysis, diagonal drop, so the Al2O3 has to go on the bottom. So I look at my equation again, and I see that I have 2 Al2O3, so I have 2 moles of Al2O3. Now, I'm ready to solve. This cancels, okay, just the unit, not the numbers, and I'm going to take 3.34 times 3 divided by 2. Round for proper sig fig, and I'll get 5.01 moles of oxygen. What I would like you to do is I would like you to pause the video and try the 2 practice problems there. Both practice problems relate to the same equation, which is right here, and it has already been balanced for you. So go ahead and pause the video now and answer those questions, please. I have posted the answers, so you should have taken your 3.84 moles over 1, and then they were specifically asking you about CO2, so that's why the CO2 is on top here, and I'm getting rid of my given, the C5H12. So I have 5 over 1, that's my balanced equation step, and then I just multiply. In the second problem, you were given CO2, so CO2 has to go to the bottom. and I wanted oxygen, so the O2 is on top in my balanced equation step here. And so I would take 2.47 times 8 divided by 5. What you'll notice here, and I like to do this because it's coming directly from the balanced equation, I didn't write the word mole for either of these. If you find that it's a lot more helpful to you to just write directly what's found in the balanced equation, that's perfectly fine. If you need to also still include the word mole, that's fine as well. So it's really kind of a preference individually. Okay? So, not too bad, hopefully. Let's move on and learn about mass. So mass stoichiometry is going to be when you're given grams and you're asked for grams. So we have to go back and we're going to need some molar masses of things to solve these types of problems. So the general equation is written here. It's going to be your given amount of grams over 1, and then 1 mole over the molar mass of the given, and then you're going to use your balanced equation step, okay, 1 over given, just like before, and then you're going to multiply by the molar mass of what you want to get the grams. So really, the only way we're allowed to compare things is through moles. So what's happening here is we're going from grams of A to moles of A. That's what this first step is. Then, we're using our balanced equation step to convert into moles of B. And then, now that we have moles, we're converting into grams of B because that's what the question is looking for. The whole purpose of stoichiometry is to take whatever you're given, convert it to moles, use your balanced equation to compare moles, and then convert from moles into whatever else you're being asked for. Okay, so we're going to do this practice problem using this general equation, and then you'll get a chance to try some. So again, the first thing you're going to want to make sure you do is that you balance your equation. So I've done that for you. And I also like to find the molar masses of these first, only because I just find it easier if I already have them. So I need the molar mass of MgCl2, which is going to be 94, and I need the molar mass of the other substance that they're asking about, which is the SiCl4. And that molar mass is 168. Okay, so now that I have my molar masses, I'm ready to plug into my general equation. So I'm given 43.1 grams of MgCl2. I'm going to have 1 mole of that MgCl2 divided by its molar mass of 94 grams. Now I'm going to use my balanced equation step. I want SiCl4. I have 1 of them in my equation for 2 MgCl2s. Okay, so that's where this is coming from. There's a 1 there and a 2. And then finally, my answer needs to be grams of my silicon tetrachloride. So I'm going to put its molar mass on top over 1 mole. These do take some practice. Okay, and then if you want, you can cross out your units that you don't need anymore. And you'll notice that you're left with exactly what you're looking for, the grams of the SiCl4. So you go through, you do the math, and you should end up getting, once you round for sig figs, very close to about 38.5 grams of the SiCl4. The next slide has some practice problems for you to try. So the equation has already been balanced. What I would like you to do is use that equation to solve both of these problems, and then we'll go over them. Pause the video now. Here are the answers to both problems. So I took the given grams over 1 mole divided by the molar mass of the given. Then in the first one I was comparing aluminum to the NH4ClO4, so it's 3 to 3. And then finally it's the molar mass of what I want. They asked for aluminum, so it's the 27 grams. The next question says how much water is produced, so I'm going to again start with my 652 grams of my given over 1 mole divided by its molar mass, and then I'm comparing water to the NH4ClO4 from the equation, so it's 6 to 3, And my final step, since I want water, is 18 grams of water, its molar mass. And again, you would go through, you would do the math and round for the proper significant figures. This does take some practice, so it is important that you also try some of the practice problems and practice worksheets that have been provided in D2L. Next concept we need to briefly talk about is what a limiting reactant is. They're abbreviated LR. The limiting reactant is the reactant that stops production because it runs out first, so it gets used up. This is not going to always be the least amount of grams. Okay, we always compare things in moles. You don't have to do the math for limiting reactants in Chem 110, but you need to know what it is, because if you need 150, you take that course and we expand upon it and actually do all the different calculations. So I have an example here. It's a burger. So we have 10 buns, 5 burgers, and 4 pieces of cheese. So we're trying to make some cheeseburgers. Okay. How many total cheeseburgers can we make? Assuming that they each get 1 piece of cheese. So you should hopefully say 4. Okay. And the one that's limiting you from producing more is the cheese. So we only have 4 pieces of cheese, and therefore the cheese is limiting our reaction. The other reactants, the buns and the burgers, would be found in excess. Most chemical reactions only have 2 reactants, so one will serve as the limiting reactant, and the other would be found in excess. The final concept that we need to talk about is something called percent yield. There's some key terms here. So the theoretical yield is the maximum or the expected amount of product that we calculate using our mass calculation. The actual yield is exactly what it sounds like, the actual amount of product in the reaction, so it's given in the problem. And then the percent yield is the ratio of the two. It's actual over theoretical, okay, so given over calculated times 100, and it will give you a percent. So let's apply this on the next slide. The real-life application of this is often pharmaceutical chemistry, among other things. So let's go through and do this example. 105 grams of chlorine reacted with excess CH4. 10 grams of CHCl3 was actually produced. What is its percent yield? So we know that we want this, and they're giving us Cl. So we're going to go ahead and do 105 grams of Cl2 over 1 mole over its molar mass of 70 grams. Balanced equation step, I want CHCl3, I have 1 of them. I have 3 Cl2s. And then finally I'm going to use the molar mass of my CHCl3. Its molar mass is 118. So I solve this just like before, and I get a theoretical yield of 59. To calculate the percent yield, I'm going to take the given actual amount of grams divided by what I just calculated, and then I'm going to multiply by 100. And you should get 16.9%. Okay, now it's your turn. Please pause the video and try the second practice problem. Here's the work for that practice problem. So I went through and I did my mass. I converted my NO into moles, used my balanced equation 2 to 2, converted into the NO2. I get that I should be able to produce 76.7 grams. And then I use my percent yield. I take the 27 grams, which was actually produced, divided by the number I just calculated, times 100, to get 35.2. This concludes Unit 2.